If you ever wondered how to create a very effective bivariate climatology maps, this is the place to be. In today's tutorial, I will reveal how you can leverage CHELSA data and then create some very crisp and informative 2D but also 3D bivariate maps of average temperature and precipitation for literally any country in the world. Our first step will be to install and download the packages that we need. There will be two packages that we will install directly from GitHub, and for that purpose we will need to install here first of all the remotes package, and for this package we'll be using install GitHub function, which helps us to install any library directly from its GitHub repo. So the first one we'll be installing is CHELSA for downloading the CHELSA climate data, and the second one is the Biscale package for creating bivariate maps. So again, both of these packages will be coming from developmental versions GitHub. Then in the second step, we'll be installing and loading the remaining packages, including these two. For that, we will be using pacman package and specifically pload function from this package. Then we'll be loading here geodata for fetching country polygons, tidyverse for data wrangling and data visualization, SF package for working with vector format, Terra for working with raster files, CHELSA and Biscale again will be simply just loading now into this R session, Elevator for fetching digital elevation model, Cowplot for putting two graphs or two maps together, Grid graphics we'll be needing to install to work effectively with Biscale. And finally, last but not least, we'll also need to install here and load Array Shader for creating effective 3D maps. All right, in our second step, we'll be accessing this CHELSA, or as I call it, CHELSA data, which is essentially climatologies at high resolution, which are hosted at a Swiss institute. And what is really cool about this data set is that it provides information for the entire globe. So we'll be downloading data for the entire globe. And it provides a resolution of approximately 1 kilometer or 30 arc seconds. So in this section, we'll be first of all defining our main working directory where we want to download the data. And then we're going to be defining a vector of IDs to download. Now, if you're not sure what exactly you need, you can also check out the codebook for this data set, where you can actually find more information about these specific IDs. So you might not want to work with temperature and precipitation like I do. Maybe you want to try out something else. So you can check out, I will drop also the link to this codebook in the description box below, so you can also check out that later. Now, for now, I know what the IDs are based on this codebook that I shared with you. So the IDs that I need are 1 and 12. So these will be for temperature and precipitation respectively. Then I'm going to write a function that is going to allow me to download this CHELSA data. The reason why I'm writing a function is that by calling CHELSA, you cannot just download whatever you want. You need to actually issue multiple calls if you have multiple IDs. So that's why I'm here putting ID at path, our main arguments in my function. And then I'm calling within this download CHELSA data, this get CHELSA data function of this CHELSA package. In the category, we want climate data. So that's why I'm choosing here clim. For the type, we want the bio data. And then for the IDs, we're going to be defining, in this loop 1 and 12. And then, of course, we need here the path as well. Once this is done, we can go ahead and download the data for each ID. We will do that by simply using the lapply, so list apply, and then we will be applying to the list of these IDs the download CHELSA data, and of course, we'll be providing for our path also this main directory that we defined. Once we download those two files, we can go ahead and use list files to inspect what are the actual names of these files so that we can load them directly into R. And as you can see here, we have actually two ones. So they both have the similar name, but the difference is in this ID that we have here. So one has a 1 ID, so that would be the temperature, and the other one has 12, so that would be the precipitation. So in the next step, we're just going to copy these two names, and then we're going to call both of them and load them as rasters into R. All right, so I just pasted them here into the editor for the sake of convenience, and then I'm going to go ahead and use Terra to load these two raster files directly into R. From there, I will be calling the rust function, which is used for calling and then transforming into a Terra-friendly format, which is spot raster. So I'm going to have here two of them. One is temperature, so this is temp, and the other one is precipitation. I'm going to just go ahead, cut and paste. So as I said, for temperature, the one that has 1 as the ID, and for precipitation, the one has 12. After that is done, I'm going to go ahead and average precipitation. So why am I doing this? The reason why I'm doing this is that the temperature we have here that we called is the average temperature for the period from 1981 to 2010, while the precipitation is the total precipitation in millimeters for this period. So essentially, because I want here to present climatology, I'm going to ahead and then average now this precipitation by dividing it by 30, because I have 30 years, right? So I'm dividing by 30, and this is going to then create my average precipitation. Then in the next step, I'm going to take this average precipitation and this average temperature, and I'm going to combine them into a single stacked raster. So essentially, I'm going to still have a single raster, but it's going to have two layers. The first one is going to be for the temperature, and the other one is going to be for this precipitation. Okay, so once we have this temp press, which is essentially combining temperature and precipitation, we can go ahead and assign names to each layer so that we know what we actually have in this one. So we're going to go ahead and do the names. And as you will see, we first go for the temperature because that's the first layer. And then we go for the precipitation. And all of this needs to be part of a list. So that's why I'm here adding C and enclosing everything with the brackets. Okay, so I would like to create a bivariate average temperature and precipitation map of Belgium. And for that reason, we actually need to define what Belgium means. So the easiest way to do that and then to crop this global data that we downloaded is to simply use geodata and then get the country polygon for Belgium. Within geodata, we can use this GADM function, and then we need to define country in terms of its ISO 3. So for Belgium, that's Bel. Level 0, meaning that's the national level for Belgium. And then we also need to define our path. And then last step, we need to convert this into an SF-friendly format so that we can easily then work together with SF and Terra. Now that we have both the country polygon and the global raster data, we're going to go and take this country polygon to crop the raster data to the extent of Belgium. So over here, what we're going to do is, first of all, define our target coordinates reference system, or CRS. I'm using here the coordinates reference system for European countries, EPSG 3035, but you can define other ones. You can go ahead and check epsg.io, and over there you can find for any country what exactly is your code. It can be EPSG, it can be ESRI. Now, once we have that, we can go ahead and crop the input raster to the country's extent and apply a mask so that we actually get only the raster for the borders of Belgium. So for that purpose, we'll be using, first of all, crop from Terra, and then we'll be passing our raster file, and then we're going to be passing country borders. Finally, we're going to also include here mask. So we want to mask actually everything that falls outside of the Belgian boundaries. After we do that, we're going to go ahead and obtain or retrieve the digital elevation model data from Elevator. The reason we are doing that is that we'll be using this digital elevation model to resample our temperature and precipitation data to a higher resolution. Remember, this one is at 1 kilometer, but we can use the digital elevation model to resample to a higher one. So what we're going to do here is we're going to convert to Terra spot raster and crop after that. So first of all, we go ahead and call get elev raster from Elevator. Then for our locations, we're going to be specifying these country borders. Z value is essentially how high resolution you want to have. I'm going to go for 8 here. Belgium is quite a small country, territorially speaking. If you're working with some larger countries, you definitely need to take a lower number. And then I'm going to be clipping here by country boundaries. That's why I'm using here locations. Very important, you also want to coerce this, convert this into a Terra-friendly format. So that's why I'm using Terra Rust. And finally, you want to crop and mask this digital elevation model. So essentially, then you have cropped and masked the climatology data and the elevation data. And then what you can do next is you can go ahead and resample the raster to match this digital elevation model's resolution. And for that, we'll be using the bilinear interpolation because our values have continuous values. They're continuous. So once we do that, we can go ahead and create actually a new object here. This is going to be resampled one. And this object is going to be byproduct of the resample function from Terra, where we need to first of all define what we want to resample. So this temperature precipitation country file. And then the second argument is what do we going to use to resample? So this is going to be the digital elevation model. And finally, we here define also the bilinear model. And then as a final step, we go ahead and project this into our target resolution, just like this. Now we can then go ahead and plot and inspect actually how this looks like using Terra plot function and then passing our object. As you can see here, we have two correct raster files of Belgium, one showing the average temperature and the other the average precipitation for the 30 years period. To be able to plot a raster file with ggplot2, we need to convert our spat raster object into a data frame. And this is exactly what we're going to do in this step. This is quite easy because what you need to do is simply use as data frame function. And doing so, we will also be creating a new object here. Now, within this as data frame, you just need to pass your raster file that you want to transform into data frame, and then also that you want to have coordinates, which means x and y equals true. Now comes the fun part, which is actually defining our breaks, color palette, and also the plot theme. We're going to go ahead and first of all create bivariate classes using the biscale package. And this is how we can do that. First of all, from biscale, we'll be using by_class function. And over here, we'll be then passing our last raster file. And then we're going to be actually not a raster file, our data frame. And then over here, we're going to be passing two dimensions, temperature and precipitation. And then we're going to be using here style Fisher, but essentially you can use any other natural interval one. You can be using quantiles, you can be using Jenks, you can be using pretty breaks. It's all up to you. And then the last one will be how many dimensions you want. This actually means how many dimensions each of your dimensions will have. So in this case, we say we want to have 3 dimensions for temperature and 3 dimensions with precipitation. That means that in total, we will actually have 9 fields in our bivariate legend scale. As a second step, we'll be defining our color palettes. Now, we'll be using one of the existing color palettes from the biscale package, and this one is called DK Blue. Essentially, this is the purple-blue color palette. I'm also going to provide in the description box below a link to the page with some more palettes, so you can check out. Maybe there are some that are more interesting to you. Now, we now go immediately to the third step, which is actually defining this custom theme for the map. And I'm going to call it, as always, theme for the win. This is going to be a function, but essentially it's going to be calling ggplot2 arguments. And the first one is the theme minimal, which means the minimum theme, getting rid of most of the stuff around. Also, I'm going to get rid of the names of the axis titles. So those for the longitude and latitude coordinates, we don't necessarily need them. Then I'm going to turn the plot background into a white one, because Ray Shader works quite well with this one, and that is the reason why I didn't use theme void, for example. It's very important here that if you are filling this background, that you use fill arguments and pass to it a color that you want, and the color arguments should not be available here. Then we can go ahead and specify some other things, such as, for example, plots title. And for the plot title, because it's a text, you need to specify here that it's element text so that ggplot2 can understand what you're actually trying to do here. And then here I'm going to go for a bit dark gray color, and I want to horizontally justify it. That's why I'm using here that h just equals 0.5. I'm going to use bold colors, and I'm going to also a bit move it down towards the map. I just copied and pasted here the plots.title, and I'm just going to add here sub. So I'm going to then create here plot subtitle as well part. And then I'm going to define how I also want to see this. Then we can also have some captions or a caption where we can define what is our data source, who is the author, for example, of the map. And we can make caption a bit smaller. So that's why I'm here taking the size of 9 pixels. And also it doesn't need to be that strong. So we take a bit lighter version of the gray color, but we do keep it horizontally justified. And we try to push it also a bit towards the map. Finally, here we also define the plot margins. And here I'm putting 4 zeros, and that means that from all sides, I'm essentially getting rid of any excess white space around the plot. And we can finally start writing the code that will create our bivariate map of average temperature and precipitation for Belgium. Now, to do that, we again call to rescue our old friend ggplot2. And we start off by first of all defining our data. And you might be surprised here that we're not using the actual temperature and precipitation data frame that we created, but we're using these breaks. That is because the breaks one has information about the bivariate scale and the distribution. That's why. But it has essentially almost the same structure. So it has the X, it has the Y coordinates, but for the fill, the name of that column is by underscore class. And then over here, actually for the legend, we don't want to show the legend. So this is a mistake. It should be show legend equals false. Now, after that, we're going to add one argument which is specific to biscale, and that is how we're going to fill the values from this bivariate scale. So we're going to be using the palette that we defined beforehand. Again, we say we're going to have 3 dimensions for each of our variables. And then it's important here that you flip axes, because otherwise you're going to have cold colors for temperature and warm colors for precipitation. We want the reverse. And then after that, you can go ahead and simply define the labels here. So the first one is the title. So we can just, say that this map is about Belgium and it's about the temperature and precipitation. And we can also add, for example, a subtitle. We can be more specific there that this is about the average temperature and precipitation for the period 1981 to 2010, which is essentially the not the last, but 30 years, so 3 decades. And then we can also include here a caption. And in the caption, we can include our data source name. And also alternatively, you can include the author name as well. So once the labels are done, we can go ahead to the last step, which is essentially adding, well, first of all, we don't want the titles for the X and Y axis, so we can also leave those empty. Now the last step is we want to define here coordinates reference system. Remember, we have that target CRS that we defined. And then in the last step, we also here add our theme for the wind, and then we complete our 2D bivariate map of average temperature and precipitation for Belgium. Okay, so we created the map and we are almost ready, but not yet, because we need to create a separate legend from our map and then to put together our map and that legend. And the legend needs to be a bivariate legend. The good news is the biscale package has an awesome way for creating legends and very straightforward. It's very easy. So from the biscale package, you just need to use this bi legend argument. Then you need to pass your palette that you're using. Then you need to pass also this flip axis if you want to flip. So we flipped, if you remember before in the ggplot2 code, and then we did not really rotate the palette. So we kept it in the same way. So this is false. And then finally, also you define the number of your dimensions, which is 3. Also, you can put here the labels for your dimensions. So the X label is the temperature in our case, and the Y label is the precipitation. We can also include here what exactly are the measures used for the temperature and precipitation. In our case, for temperature, this is Celsius degrees, and for precipitation, it is millimeters. And then as a final argument here, you can also include what is going to be the size of your legend, and I chose here size 8, but you can go ahead and play and see what exactly is the size that works best for you. All right, so we got a map and the bivariate legend. Now we can go ahead and combine the two into a single plot. And now we're gonna use one of the tricks, which is the cow plots package, which is awesome for really combining graphs and maps, whatever you wish, as a byproduct of ggplot2. Now from cow plot, we can use the ggdraw one, which essentially is gonna grab our objects, our map and our legend. It's going to plot them. and then it's going to combine them together. So draw plots does that for you. So in the first one, what we're doing here is we're defining that our first plot is the map. Now we're also defining 4 more very important arguments here: X and Y and width and height. X and Y is essentially, are you going to move your plots alongside the Y and X axis? If you're saying here no, so 0, then it means you're not moving. Width and a height here is nothing more than a ratio. So width and height can go from 0 to 1. This essentially means is what is going to be the ratio of your plots. And I'm saying here 1, which means 100%, or I'm not going to be downscaling at all. I'm going to take it as is. Now, apparently, or obviously, we also need to now add another plot, and this is going to be our legend plot. Now, legend plot cannot be the same size as the map, because then it's going to overlap. It's going to maybe even go over the map. So we need to do a bit of a downscaling here. So after we define here that our second plot is that legend object, for X, we're going to, and for Y, we're actually going to take very small values. What does it mean? That means that we will want to have our legend in the lower left quadrant of the screen. That is because the low x-axis and the low y-axis is going to position there. If you, for example, took a very high x-axis and very high y-axis, it will put you into diagonally different part of the screen, which is the upper right quadrant of the screen. So this essentially is like in ggplot2. It defines where your plot is going to be. And then with the width and the heights, as I said before, we need to downscale here. So instead of taking 100%, in this case, as you can see, we're going to be taking 25%. So 0.25, in other words. What is also important is because we're having here 3 by 3, we also want the width and the height to be the same. So they're not going to be stretched. And that's why over here, whatever you use, whether you use 0.25 like I do or something else, make sure if you have 3 by 3 that you take the same size for the width and the height. And as we create this full map, we can go ahead and plot the results or display the final results, the final map. And that is, again, quite easy. We just need to use print from base R and then just pass this object to it. And here is our 2D map of Belgium's average temperature and precipitation for that period of 30 years. What you can see here is the map of Belgium colored in the palette, which shows 2 things actually. Well, temperature is associated with warmer colors, while precipitation is associated with colder colors. So what you can see is you can see the trends in the legend itself. So the warmer the color is, the more there is temperature, and the colder it is, or it becomes lighter, more lighter blue or towards green, then you have more precipitation. Well, where these two actually match is this navy blue color, and this is where you have a lot of temperature, or like a higher average temperature, but also a higher average precipitation. You can also see that I kept the graticules on the side together with the grids, which you can also remove, but I also noticed that a lot of people watching my videos are asking to also be able to represent those. But that's not all. You can also go ahead and save this map as an image file, or in this case, I'm going to be saving it as a PNG file. And for that, I will be using ggsave. Then I'm going to be passing here, first of all, the file name I want. Very importantly, you need to also provide here .png, so the PNG extension. Once you do that, you can go ahead and define the width and the heights in inches, which is very important here. So inches, I'm using 7 by 7. And after that, you can also define this number of points, so 600, so that would be the resolution. Again, the device is PNG, is just confirming. The background is going to be white, you can change this. And again, here we're providing the name of the ggplot object that we want to save locally. We're done with 2D bivariate mapping, but we are just getting started creating 3D bivariate map. Now, to do that, we are going to use one of the old tricks from one of the previous tutorials on creating 3D land cover maps, where we actually use the terrain layer as an invisible layer to create a 3D effect. So essentially here, we're going to be having the bivariate part of the map represented with the color. And then the 3D effect will be represented using, of course, ray shader with shadows. Now, to do that, we need to go back to our digital elevation model file that we downloaded. And then we need to turn it into a data frame. Well, first of all, we need to reproject it into the appropriate coordinate reference system. And then we need to turn it into a data frame. So to reproject it, we'll be using project from Terra, and then passing our target CRS. And then we're going to be using as data frame for turning this raster file into a data frame. Again, X and Y equals true is going to be there. And also importantly, we're going to remove any missing values. So that's why I'm using na.rm equals true as well. Okay, so once this is done, we can go ahead and rename the third, so the value column or the digital elevation model value to DEM. And we can just pass this names from base R and then assign this DEM to our third column. So once we do that, we can go ahead and create our terrain layer map in ggplot2. Even though this map is going to be simply white, it's going to be useful in the next stage where we're going to be using ray shader to create a 3D map. So we go ahead and use ggplot2 here. We pass the DEM DEM_DF. We pass also the X, Y, and fill values. We use the geom raster because this is essentially a raster that we are here plotting. Scale figure gradient is going to be used because we have the continuous values, which are the digital elevation model values. And then for the colors, we're going to be just using white here. And then in the guides, what is very important here is that you want to omit the legend. So that's not needed. You don't want that to appear in 3D render. But for the labs, the trick is to use all the labs that you also used in the previous map. And you can even write here the same names of these maps, just like I'm going to do here. Or you can just go and copy and paste. So for the title, we're going to reiterate that we're dealing with temperature and precipitation. For a subtitle, again, we're just specifying it's about the 30 years period. And also for the caption, we're going to be including here the data source name, and optionally also you can include the author name. And of course, you can leave the X and Y axis empty in this case. Again, what is very important here is that you leave the colors white, so the color of the digital elevation model, that there is no legend, so you need to omit it, and then repeat all the labs or labels that you had in previous one, you also need to have here. Same goes for the coordinate reference system. You need to use the same one that you used before. Otherwise, if you don't use the same, there's going to be discrepancy, and you will notice that on your 3D map. And finally, what you need to do here is call theme for the win. And then as a separate theme, again, make sure that the legend position in this case is none, so that no legend is going to be shown in the final 3D render. And then we can just go ahead and render our 3D scene. For that, we'll be calling a ray shader, and we'll be calling plot.gg function from ray shader. Within this one, we need to specify what is our main ggplot object. So that would be that full map with the bivariate scale and bivariate legend. And we need to specify the second one, which is going to be what is the height map. So this is going to be the digital elevation map that we created. This one is going to create the effect of the 3D render. For the width and heights, here you need to specify in inches. So we're going to be using the same as for the 2D map. And window size in reverse, you need to use pixels. So 600 by 600. Notice here how I'm using the same ratio. So because I used the same for the width and height, window size also needs to follow the ratio. Scale is how high these spikes are going to be. And I'm going to be using just 100. 100 is default one, but you can see what works for you. For the shadow, I'm going to be using shadows, but the shadow intensity is going to be low. So that's one value. I'm going to be using degree angle of 87 degrees. I'm not going to be tilting around the axis, so that's why theta is 0. And for the zoom, I'm going to try with 0.56. So that's kind of a middle zoom here. And finally, I'm going to be using the multi-course here for faster processing. So you will notice that we are actually missing a bit from this render scene. So we can go ahead and readjust this so that we can see the entire scene. And to do that, we can use from ray shader a function which is called render scene. Within this scene, you can change, for example, this phi value, theta, or zoom. We can just go for changing the zoom value and taking, for example, 0.6. So we readjusted the scene, and we can now go ahead and download from Polyhaven, which is really a treasure island of so many different customized light files. So I'm going to go for this Brown Photo Studio 2, which I usually use in my tutorials. But I will drop also the link to Polyhaven so you can explore maybe some other lights. And then I'm going to go ahead and I'm going to grab the name of this file from this URL. And then I'm going to go ahead and download this Polyhaven file locally by specifying the URL, the destination file name, and also the binary mode as the way of downloading this file. And we're finally ready to render our 3D map as an image object. So we can go ahead and call a render high quality from Ray Shader. Within this one, we need to specify several attributes. The first one will be the file name, and I want this to be saved as a PNG file. So I need to specify the name of the file together with the PNG extension. After that, also I would like to see as the scene gets rendered, so the preview will be on. Light will be off because I want to use the environment light. And for the environment light, I'm going to be using the name of that file that I downloaded in the previous step. Then I can also define what is going to be the intensity of this lighting. And for that, I'm just going to go for a default 1. If I want darker a scene, I'm going to go for a lower value. If I want lighter, I'm going to go for higher than 1. And then I'm also going to make sure that the environment of this light is rotated to 90 degrees so that the shadow appears somewhere at 90 degrees. I also want to use here the parallel sources so that, again, the computation is faster. And I'm not going to exaggerate here with the width and height. I'm going to be using just the 2000 by 2000 pixels. If you want a crisper image, you can also increase that. And finally, I'm going to be turning off the interactive mode. All right, folks, this is how you can leverage CHELSA data to create some awesome bivariate temperature and precipitation maps for literally any country in the world. And the best news here is that you can also create both 2D and 3D maps with the help of Ray Shader and ggplot2 in R. I'm really looking forward how you take this tutorial on a journey across the world and start creating some awesome maps. So feel free to share your experiences, but also questions or any comments you might have in the description box below. Also, if you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do check them out. See you next time.